Hello everyone, welcome to Concepts of Physics with Irfan. Students, last time we discussed vector products, right? And we even studied some of the cases of vector product. So next we are going to move toward the next half of this chapter, that is about equilibrium. But before going toward equilibrium, there are few basic concepts which are very important, and we are going to go through those basic concepts. The first one is concurrent forces. Now students, let us say that if we are having a point P and three different forces, let's call that F1 is acting along that direction, F2 is acting along this direction, and another force F3 is acting along this direction. So we are having three different forces which are acting along three different directions. But if all these three forces, if they act at a single point, then such forces are what we call concurrent forces. So we can define concurrent forces as two or more forces that acts at a single or common point. So when such forces which act at a single point, then the line of action of these forces will be passing through a common point. So all these forces will be having a single line of action, right? So we can write that these forces will be having a common line of action. Okay, right. So if three students, they apply force on a single point object, in whatever direction, no matter whatever direction they are going to apply, but if the point of action of all such forces is same, then such forces can be considered as concurrent forces. Another fact about concurrent forces is, if we are having more than two concurrent forces, two or more than two concurrent forces, then we can replace, or we can balance such concurrent forces by a single force, and that single force will be equal to the magnitude of resultant of such concurrent forces, but its direction will be opposite. So let's say that we are having two forces, F1 in that direction, right, and F2 is perpendicular to F1 in this direction. And let's say that the magnitude of the first force F1 is 763 Newton. 763 Newton. And this is actually acting along positive x-axis. F2 is acting along positive y-axis. And let me extend the x and y axis, right? So this is y prime, this is x prime. Okay, now you can see that both these two forces, they are mutually perpendicular, and let's say that F2 has a magnitude of 525 Newton, 525 Newton, and both these two forces are perpendicular. Now we can find the resultant of such two forces by following head to tail rule. So let's say this is F2. I am going to place F2 in such a way that its tail will be on the head of F1, right? And then in order to find the resultant, as this is the origin and the tail of F1 start from the origin, right? So we have to join the tail of the first vector with the head of the last vector. So this will be our resultant force. It has to be a kind of straight arrow. Okay, so this will be the resultant force F pointing in this direction. Okay, so this is actually F2, right? So F2 is 525 Newton. Okay, now you can see that after drawing the resultant force, we can even find the angle theta which the resultant force is going to make with the x-axis. Okay, this resultant force is actually the effectiveness of both these two forces. So let's say that if we are having a point over here, so the force F1 was pointing in that direction, right? So let's say that this is a point object and two forces are being acted upon that point object. So F1 in that direction and F2 in this direction. So F2, this arrow has to be somehow larger than F2 because the length of the arrow actually represents its magnitude, right? So now you can see that F2 is directed upward, F1 is directed toward right. So as a result, this point object is going to move in that direction because both these two forces are going to produce a net effect in this direction, and this is what we call the resultant force F. Okay, now as I mentioned that we can balance such concurrent forces because both these forces, they are acted upon a single point, right? So they are concurrent. By definition we can say that they are concurrent. So such concurrent forces can be balanced by a single force, and that force is what we call equilibrant force. Okay, so two or more concurrent forces can be balanced by a single force. This is the definition of equilibrant force. Single force called equilibrant force. Okay, now let's see how we are going to find this equilibrant force in this case, right? Okay, now it's easy to find the magnitude of the resultant force. So for that I can find its magnitude. This is y prime. Okay, so the magnitude of the resultant force F, as it is a kind of right angle, and we have discussed that we can find the magnitude for a resultant force by taking the square root of summation of square of the individual forces. So F1 square plus F2 square. So after replacing these values and doing some calculation, we can find the magnitude of the resultant force, and it will turn out to be 926 Newton. Okay, now this is the magnitude of the resultant force. What about its direction? And that direction we can find it using this angle theta, right? So it is actually representing the direction of the force. We know that the angle theta can be found by tangent inverse of y component of this resultant over x component. So in this case the y component is F2 and x component is F1. So we can simply write F2 over F1. So again, after doing some calculation, we are going to find that the angle theta is 34.5 degrees. So this angle here, it is 34 point. So let us write 34.5 degrees. So the resultant force is going to make an angle of 34.5 degree with the x-axis. Okay, now as we know that such concurrent forces can be balanced by another force or a single force, and that single force what we call equilibrant force, and this equilibrant force, it will be having the same magnitude as the resultant force, right? So there are two properties of such equilibrant force. Its magnitude will be the same as the resultant or the net force, but its direction will be totally anti-parallel or opposite to the resultant force. So we can draw a force in this direction. I hope that it looks like anti-parallel, right? So this will be a kind of equilibriant force. You can see that it is totally anti-parallel to the resultant force, and let's call it Fe, equilibriant force. As you can see, it is pointing totally opposite, right? So as from this figure, if such two forces are acted upon a point object, the point object is going to move in that direction. So we can restrict its motion by applying a force having the same magnitude as the resultant but in opposite direction, and that force what we call equilibriant force. So this force will be having the same magnitude as 926 Newton. That is the magnitude of the resultant force. What about the angle theta, as it is totally anti-parallel to the resultant? So this angle over here, it will be 34.5 degree, but the angle theta can be found as it is lying in the third quadrant. So we know that we measure angle from the positive x-axis. So from here to here we are having 180 degree. So the angle theta would be 180 plus 34.5. So the angle will be 200 and I think 14.5 degree. 14.5 degrees. So this will be the direction of the equilibriant force. So no matter how many concurrent forces are there, we can balance all concurrent forces by only a single force, and that force is what we called equilibriant force, right? And for finding out the equilibriant force, we need to find out the net or the effective component of all such concurrent forces. Okay, so if three students, if they are going to apply a force on an object in different direction, and eventually the object is going to move in any particular direction, right? So we can restrict its motion by applying a force in such a direction that its direction will be opposite to the direction of motion, and the magnitude of the force has to be equal to the net effect of the magnitude of all these concurrent forces, right? So this was all about concurrent forces and equilibriant force. Next we are going to discuss torque. Students, so next we are going to study torque. Torque can be defined as the turning effect produced in an object or in a body about a fixed point. So this is important, about a fixed point, and this turning effect is produced due to an applied force. So about a fixed point due to an applied force. So such an effect is what we called torque. So this is also called moment of force, right? Okay, so whenever we are going to apply a kind of force on such an object which is fixed from a single point, and that fixed point is actually its axis of rotation, right? So if we are going to apply a force on such an object, and as a result if the object start rotation, then this effect is what we call torque, and this effect is produced due to the applied force, right? Okay, let us take an example of a wheel, because we know that a wheel actually rotate due to an applied force, and this is the center of the wheel and what we call axle, right? So this is the axle of the wheel, and let us represent one of the spoke of the wheel with this line, okay, and we call this distance as r. Okay, now if we apply a force at this point in this direction, and let's call that force as F. So let us say that this is O, the axis of rotation, or in this case, in case of a wheel, it is the axle, right? And here this is the point of impact of the force, and we call it as point A, right? Okay, now the force is acted in that particular direction, and from our common observation we can see that after we apply a force on a wheel in that direction, so this wheel, it is going to rotate, right? And the rotation will be in that particular direction. Obviously it is anti-clockwise rotation, so rotation will be anti-clockwise. Okay, and on the other hand, if we apply force in this direction, so a kind of clockwise rotation will be produced, right? It is represented by Greek letter ta, and it is a vector quantity, so we have to use an arrow above such a symbol. Okay, now this torque, it is dependent upon two variables. So from the figure you can see that we are having a kind of distance between axis of rotation and point of action, and this distance is what we call moment arm. So this is the first variable, and then other variable we are having is the force or the applied force, right? So torque is going to depend upon these two variables. Okay, but before I am going to write the definition of momentum, let us see that, as this force, it is not perpendicular to the moment arm, right? So it is actually making certain angle, and that angle we call theta, right? So we can resolve this force into its component along the direction of the moment arm and perpendicular to the direction of moment arm. So by dropping a kind of perpendicular, so we can resolve it. So this component, so let us say that this is the point A over here. So this component, it will be F cos theta, so from right angle triangle, and this component will be F sin theta. Okay, now if the force will be acted along the direction of the moment arm, there will be no rotation produced, right? So on the other hand, if this force will be along the perpendicular component of the force, then obviously it is going to rotate. So from our observation we can say that this component of force play it doesn't play any role in such kind of turning effect, right? So it has zero effect on the rotation of the wheel. On the other hand, this force is the only force responsible for producing rotation. So let me draw this over here. So this is actually the force responsible for producing rotation. So this was actually the net force, right? So the effective force is this one, so the perpendicular component of the force. Okay, now from here we can see that the reason why we are having rotation is F sin theta, the perpendicular component. So actually the two variables that define torque is the moment arm R, and it is a vector quantity, and the other one is the component of force perpendicular to the momentum. So in this case we are having F sin theta. So torque will be equal to R times F sin theta, and as it is a vector quantity, so let us write a kind of unit vector, okay, in order to represent its direction. Okay, so students, next is from this equation, let's call it A. So from equation A you can see that we are having a kind of trigonometric ratio sin theta over here, and this sin theta appear whenever we are going to take cross product of two vectors. So we can say that torque is actually the cross product of moment arm and applied force. So even we can write that torque is the cross product of moment arm and applied force. So once we will open this cross product, we are going to get the same equation. Okay, now R, this R, it is what we called moment arm, and this moment arm is the perpendicular distance between axis of rotation to the point of action of force. Okay, so this is what we call moment arm R. So it is a kind of vector, right? It is actually a position vector between point of action of force and the axis of rotation. Okay, now is from equation A we can see that we are having three variables R, F and theta. So there are three different factors which are going to affect torque. So the factors which are going to affect torques are, what are the factors? So the first one is, okay, let us take an example that if you are going to open a door, right? So, while opening a door, we are actually producing torque. We are actually rotating the door, right? About its axis of rotation. And obviously the axis of rotation will be the point from where the door is attached, right? With the wall. Okay, now if you apply more force, you can easily open it, and if you apply a very tiny magnitude of force, it will open slowly, or the turning effect will be low, right? So greater will be the force, large will be the turning effect, large will be the value of torque. Smaller will be the magnitude of force, less will be the turning effect, and small will be the value of torque. So the first factor is magnitude of force. Magnitude of force. Let me only write its symbol, okay? Now, what about the second factor? The second factor is obviously moment arm. Okay, so if we are going to try, if we are, if we want to open a door by applying a force close to the axis of rotation, so it will be hard, right? On the other hand, if we will apply force away from the axis of rotation, we can easily open such a door, right? So what we are going to do is, actually we are going to change the moment arm. In the first case, the moment arm is small. We are applying force close to the axis of rotation, so the perpendicular distance is small, so more effort will be required, right? Now, if we are going to move the point of action away from the axis of rotation, so the moment arm is going to increase, so less effort is needed in order to open such a door, right? So from this observation, we can conclude that if we are going to increase momentum, more torque or turning effect will be there. If we are going to decrease momentum, less turning effect will be there. We can take another example. If we try to open a kind of nut using a small spanner, more effort will be required. On the other hand, if we use a large spanner, right, so with less effort we can untie such a kind of nut. And again, the reason is large spanner is actually giving us large value of momentum, right? So it depends upon the magnitude of momentum. Magnitude of momentum, in this case we represent it with R, right? And the last factor which is going to affect torque is the angle theta, because if we apply force along the direction of the moment arm, no torque is going to produce, right? So it is because that this angle is actually affecting the torque or the rotation. So the third thing which is going to affect torque is angle between R and F. So from here, the first case is, if theta is equal to 90 degree, what does it mean? If the force is perpendicular to the moment arm, at that time this sine 90 gives us 1 and we get maximum value for torque. So torque will be maximum, okay? Now, on the other hand, if the angle is 0 degree, so if we apply a force parallel to the moment arm, so no turning effect will be produced, right? So for such a case, the torque will be 0 and that is the minimum value, right? So for maximum torque, we need to apply force perpendicular to the moment arm, okay? So this was all about torque or moment of force. I hope that now you can understand the concept behind these two topics, torque and concurrent forces. These are important in a sense that we are going to need these two concepts in order to understand equilibrium and the conditions for equilibrium, right? So in the next lecture, we will be discussing equilibrium, its different cases, and the conditions which are necessary for maintaining a kind of equilibrium. Thank you. See you in the next lecture.